Okay, so let's get started. I'll start with a summary that's a little bit more general than just what we did on Tuesday, so that I cover also the main things that you need to know for assignment 5. So then we'll finish the lectures or the material in chapter 7, and then we'll work on the assignments. Michelle will do one problem, and I'll do another problem as an example, and then you guys can work on the assignment itself. So summary. Let's go back to chapter 5 and recall what we did there. So in chapter 5, we found that there was a connection between symmetries in the Lagrangian and conserved quantities. In particular, for a continuous transformation, of the coordinates. So you can write a continuous transformation by saying coordinate qi primed is the original coordinate qi plus some coefficient fi that could depend on the qi's times a small thing, delta epsilon. This is an infinitesimal transformation, so it's part of the continuous transformation. It's continuous because we just make delta epsilon bigger, and then qi prime is more different from qi. In principle, each qi has its own little factor, fi, that multiplies the delta epsilon. And we did 2 examples of that specific transformation in chapter 5. We did rotation about the z-axis and translation about the x-axis. And we saw that both of those transformations could indeed be written in this form, and we figured out how to figure out what the fi was. It was not super straightforward to get what the fi was for the transformation, but we saw that if we're careful, we can figure out what they are. And in general, you can figure it out for a general transformation. We also had we allowed for time to also be transformed, and so we said the transformed time was the original time plus some factor g times this delta epsilon. So we treat time just as any other coordinate, and we say that in principle we can have a new coordinate system where time is also transformed. And so we said that the little factor that goes with t is g instead of f. And so Noether's theorem said that if the action is unchanged with respect to a continuous transformation, then the quantity q, which was given by the sum over the degrees of freedom, I equals 1 to n, of fi multiplied by pi, where pi is the conjugate momentum to coordinate qi, We also found that from the Lagrangian, we can write that as diL by diqi dot. So this quantity Q is given by the sum over the Fi Pi. And then there's a second term. Let me just get my notes so I don't write it out wrong. It was plus G times the sum of I equals 1 to n of Pi Qi dot minus L, which we recognize that term in parentheses to be the same as a Hamiltonian if everything is written in terms of P's and Q's, or the Jacobian rho in general. Okay, so if the action is unchanged, or the action is the integral of the Lagrangian, with respect to a continuous transformation, then Q is conserved. By conserved, we mean doesn't change with time, and mathematically that means that dq by dt is equal to 0. So those, you should really be thinking those as synonyms. Something is conserved means its total time derivative is 0. Okay? So that's the general statement. If the action is unchanged with respect to a continuous transformation, so to check if the action is unchanged, you have to calculate delta S. So you have to calculate S using the Q's, and then S using the Q primes with that transformation. And if S using the Q's minus S using the Q prime is 0, then S is invariant to that transformation, then the quantity Q is conserved. So if the action is unchanged, or to say if the Lagrangian is unchanged under the transformation, then naturally the action, which is the integral of the Lagrangian, is also unchanged. So often, you only need to check if the Lagrangian is unchanged by the transformation. So we saw two specific cases of that. One is if L does not depend on one of the QIs, then we found that the conjugate momentum of QI was equal to a constant, or was conserved. So that falls naturally from the quantity Q, right? Because you would just have one of the F's be equal to 1, all the other F's and G equal to 0. So the conserved quantity is Pi. But this also falls out from the observation from the Euler-Lagrange equation of the cyclic coordinate. So recall the Euler-Lagrange equation, which says that d by dt of diL by diqi dot minus diL by diqi equals 0. So if L does not depend on the one of the QI, that means that diL by diqi is 0. The thing that we have here in parenthesis, that's equal to Pi, right? So you really have d by dt of Pi equals 0. Of course, d by dt of something equals 0 means that Pi is conserved. similarly, we also had to, if L does not depend explicitly on time, then the quantity that we call the Jacobi integral, the sum from I equals 1 to n qi dot pi minus L, is also equal to a constant. So the first one was, if L is invariant to translations in the direction of qi, then the momentum in the direction qi is conserved. And the second observation is that if L is invariant to translations in time, then the conserved quantity is usually equal to energy. Okay? So that's sort of a high-level summary of Chapter 5. Any questions about that? Okay. Next, we introduced the Hamiltonian. H. And so H is a function of the pi, the qi, and t, is defined to be the sum from I equals 1 to n of qi dot pi minus L. So it's very much like the Jacobi integral lowercase h that I wrote above. However, what's very important to note is that the Hamiltonian H has to be written in terms of only the QIs and the PIs. So H does not depend on the QI dots. Of course, when you do this transformation, you explicitly end up with QI dots because the sum has QI dots in it, and then L presumably also has QI dots in it. So you must, after you evaluate the expression for H, you must always eliminate the QI dots from the expression for H. Okay, and we showed explicitly that you're always able to do that. It's one of these properties of the Legendre transform. The Hamiltonian is a Legendre transform of the Lagrangian. Found in the Hamiltonian formalism, the equations of motion are given by 2n what we call canonical equations. So we say that the qi and the pi are canonical variables, and the equations of motion, there's one for all the QIs, and there's one per QI, and then there's one per PI, right? And there's the same number of QIs as there are PIs, and so there are 2n equations of motion. We call those the canonical equations. And the canonical equations have a particularly simple form. One gives us the time derivative of qi dot, and that's found by taking the partial derivative of the Hamiltonian with respect to pi. And the other equation of motion tells us the time derivative of the pi, and that's given by minus the partial derivative of the Hamiltonian with respect to qi. Okay? Any questions about that? And then finally, we introduced Poisson brackets. And these are related to the commutators between operators in quantum mechanics. So the Poisson bracket between two functions u and v is defined to be the sum over the number of degrees of freedom, so I equals 1 to n, and the way you do it, you go di the first function, so di ui by di qi, times di v by di pi, minus di v by di qi, di u by di pi. So these Poisson brackets are a little bit annoying to calculate, right? Because you have to do this sum over n terms of these four partial derivatives, two products of two partial derivatives. However, we're able to do a lot of things with these Poisson brackets without even ever having to evaluate these sums. So we found that we can write the canonical equations using Poisson brackets. The canonical equations were already pretty simple, but then you could easily maybe forget that which one has the minus sign. And so using Poisson brackets, they're even more symmetric and pretty. So using Poisson brackets, the canonical equations are, so first you need to know what qi dot is. And you can find qi dot simply by taking the Poisson bracket of qi with the Hamiltonian. And similarly, you can do that for pi dot. That's given by the Poisson bracket of pi with the Hamiltonian. More generally, if we have a function f that's a function of the canonical variables, qi, pi, and t, we found that the total time derivative of f was given by the Poisson bracket of f and the Hamiltonian. And if f depended explicitly on time, we have to add this di f by di t in it. So we see here that the Poisson bracket of something with the Hamiltonian is related to how something changes with time. Right? If you look at qi dot, pi dot, those are both telling us how q and p change with time, and they're both given by the Poisson bracket with the Hamiltonian. And then this generalizes to any functions of the q's and p's. And then in fact, this last relation is one that comes up in quantum mechanics to find out in the Heisenberg representation how an operator changes with time. And in quantum mechanics, you have two ways of doing things. The Schrödinger way, where the wave function depends on time, and you operate on it to get various observables, or the Heisenberg representation where the operators change with time, and well, we don't call it a wave function, we call it a state vector in the Heisenberg representation, but it's the operators that change with time, and the system is described by a constant state vector. So today I want to finish the chapter and go into a little bit more of these neat properties of Poisson brackets. So we already see here the Hamiltonian, remember, is often equal to the total energy. So we are seeing some relationship between how something changes with time and the Poisson bracket of that something with energy. So we already see again the relationship between conservation of energy and time. Because if the Poisson bracket of something with the Hamiltonian is 0, then d of that something by dt is 0, and that something is conserved. Obviously, if something's not conserved, it depends explicitly on time. So by f by dt would be 0. The last little section is on Poisson brackets and symmetries. So recall in chapter 5 the infinitesimal transformation or rotation about the z-axis. So we found the coefficients Fi that correspond to a rotation about the z-axis. So we found in particular that x prime was given by x minus y delta epsilon. So the coefficient Fi that goes with x was minus y. Right, I'm rewriting these transformation equations here, as I said in the beginning, specifically for the case of rotation about the z-axis in Cartesian coordinates. So we found that y prime was given by y plus x times delta epsilon. So the coefficient Fy was equal to x. And then z prime was equal to z. Right, so rotation about the z-axis leaves the z coordinates unchanged. So fz was equal to 0. And then this, so if the Lagrangian is invariant to this leads to a conserved quantity. This led to a conserved quantity Q, which was given by the sum over I of Fi Pi. We're going to forget about the G term with the time, since we're not transforming time here. So this led to the conserved quantity. So there's only two of the F's are non-zero, right? So we have Fx, which is minus y times x. We have minus xy, sorry, it's minus x times py. Isn't that right? And it's fx times px. It's minus y times px, yeah. And then it's plus fy, which is x times, no, sorry, I'm writing it wrong. I don't know why I'm writing it wrong. Minus y times px plus x times py. That's fx, and that's f1. And that is the z component of angular momentum. So if the Lagrangian is invariant to rotations about the z-axis, then angular momentum about the z-axis is conserved. Okay? So now let's look at this with Poisson brackets. Now consider the Poisson bracket of the coordinate x with the z component of angular momentum. So it's the coordinate x with the z component of angular momentum, which is x times py minus y times px. Now you have to go back and look at equation, I want to say 737. So if you look at equation 737, we had a bunch of properties of Poisson brackets. Okay? I'm going to use those properties. In particular, I'm going to use that property to split up the first sum. So I can write this as the Poisson bracket of x with x times py minus the Poisson bracket of x with y times px. And part of the assignment is you're going to prove these. Okay, so I can split this out even more. I'm going to take out, in the first one, I'm going to take out the first x, the second x, so I have it there. I have x with py. Oops. Sorry, wrong button. I have x with py plus py times x with x. And then I split up the second term. I'm going to bring the x out, so I have minus y. I'm going to bring the y out. I have minus y times x with px, that comma, minus, now I'm going to bring out the px, and I have px and x with y. Okay, so I'm using the properties from equation 737 that tell us how to break up sums and products inside of Poisson brackets. So that's equation 737. I'm going to look at the final properties from equation 737 that tells us we now have Poisson brackets between coordinates and conjugate momenta. So in particular, we found that the Poisson bracket of the coordinate with the coordinate is always 0. And that falls from the definition of the Poisson bracket, right? Poisson bracket of something with itself is always 0. And the Poisson bracket of a coordinate with a different coordinate is also 0. So they're independent of each other. Then we found the Poisson bracket of a coordinate with a conjugate momentum that's not the one conjugate to that coordinate is also 0. And then finally, we found that if we take the Poisson bracket of a coordinate with the momentum that's conjugate to it, that was equal to delta ij. So it's equal to 1 if it's a coordinate with its conjugate momentum, and 0 if it's the coordinate with not its conjugate momentum. In this case, it's x and px, and so that's equal to 1. So finally, this thing is equal to y, minus y. Sorry. Okay. So one can easily show I'm going to rewrite the one we just had. So the Poisson bracket of x and LZ is equal to minus y. You guys can still hear me, right? There's some static here. The Poisson bracket, it's easy to show that the Poisson bracket of y with LZ is equal to plus x. And it's easy to show that the Poisson bracket of z with LZ is equal to 0. So why is this interesting? We go back and we look at the transformation for rotations about the z-axis. We found that fx is equal to minus y, fy is equal to x, and fz is equal to 0. Here we found that the Poisson bracket with the quantity that's conserved gives the coefficient for that transformation. All right. So the Poisson bracket of the coordinate with angular momentum give the coefficient of the transformation that leads to angular momentum being conserved. We say that LZ, angular momentum about the z-axis, we say that is the generator of rotations about the z-axis. And that's a very interesting result. So it appears that if you know that there's a conserved quantity, you can find the transformation that leads to that conserved quantity by using the Poisson bracket. So you can find the momentum. The same thing happens if you take x, y, and z Poisson bracket. Or if you take the momentum components, px, py, and pz, with lz, and you'll find that you also get how momentum transforms under rotation, and transforms the same way as x, y, and z. So you get the same coefficient. And there really is a deep connection between the transformation that leads to a conserved quantity and the Poisson bracket of the coordinates with that quantity. let's do another one. Let's do linear momentum. So for linear momentum, we found that was related to translations. And has to do about the x-axis. Of course, it works translations along any axis. I guess I should say along instead of about. I hope that doesn't sound too Canadian. So the transformation equation for linear momentum, or translation along the x-axis, was that x prime goes to, well, let me just write it as x plus delta epsilon. So fx was equal to 1. Then we had y prime was equal to y, d prime is equal to d. And so fy was equal to 0, and fz was equal to 0. So we know that the conserved quantity, Q, was given by Px. Now let's flip it around and see if we can figure out, given that the quantity that's conserved is Px, can we figure out the coefficients of the transformation? So can we figure out Fx, Fy, and Fz? So we should be able to consider the Poisson bracket of the coordinates with Px. So what happens if we do x and Px? Well, that's evaluated trivially, right? If we look at the relations, that's just equal to 1 because x and Px are conjugate. Now, of course, if I take y with Px, since they're different, it's going to be 0. And if I take z with Px, it's also going to be 0. And so that really is Fx, that really is Fy, and that really is Fz. So far, I've only looked at how the coordinates transform, but that's generally true for any function of the coordinates. So, for a function f that depends on the coordinates and their generalized momenta, the Poisson bracket of a function and momentum is given by df by dx. You can look that up in equation 737. So under an infinitesimal translation, if I move the x-axis a little bit, then f will be a little bit different, and I'll call it fi prime. That's just going to be the original f plus the derivative of f with respect to x multiplied by delta epsilon. Right, if I translate the x-axis, how is f changed? It depends on how f depends on x. So it depends on x by df by dx. But we can also write this in terms of Poisson brackets. So instead of saying f goes to f plus df by dx, I can just say f goes to f plus the Poisson bracket of f with px. So taking the Poisson bracket with the momentum in the x direction tells us how something transforms when you do translations in the x direction. So it's going to take a little bit of rereading this to really wrap your mind around all of this. So let's finish this up with So we've done rotations and translations. So let's do translations in time. So we've made the argument that if we know a conserved quantity, I can take the Poisson bracket of that conserved quantity with something to know how something transforms under the transformation that makes the thing conserved. So in particular, I know that if energy is conserved, then I should end up with time translation. If energy is conserved, then the Hamiltonian is usually equal to the energy. If I do the Poisson bracket of something with the Hamiltonian, I expect it's going to tell me something about how that thing transforms under time translation. In fact, we've already explicitly said that, right? What was that? That was this last function here, how df changes with time. But there we weren't really talking about transformations, we were more considering just the total time derivative. So we see that it actually is related to time translations as well. So we know that if the Hamiltonian is invariant to time translation, then H is conserved. Of course, that's a little bit redundant, right? And it's only redundant because the Hamiltonian has this amazing property that di H by di T is equal to dH by dt. Remember. So in that case, of course, if H doesn't depend explicitly on time, H is conserved. That's a roundabout statement. Say exactly the same thing because of that property. All right. So consider Poisson brackets with H. So in particular, let's consider what the transformation would be, what f prime would be if I take f plus Poisson bracket of f with H. I'm sorry, that should be, maybe we'll call it a dt this time. No, we'll call it, no, sorry. So this tells us how f transforms with time. I should probably call it delta epsilon so that this thing here altogether is delta t. No, I'm not going to say that. I'm just going to leave it the way it was. Yeah, so that's pretty interesting. And so of course, if the Poisson bracket of f with the Hamiltonian is 0, then f does not change with translations in time. We can now turn this around and stop thinking about conserved quantities. And we can just ask ourselves, we can just build new transformations. So consider a general function g that depends on our canonical variable. I call it g for generator. So we can define a new transformation where Qi primed is given by Qi plus the Poisson bracket of Qi with G, whatever G may be. Oops. And we can define Pi prime to be Pi plus the Poisson bracket of Pi with G. So we can take any function that we want, and if we take the Poisson bracket of that coordinate with that function, that's going to lead to some transformation. Now, it might not necessarily be a conserved quantity or anything, but in general, this is something that we can do. And we call G the generator of this arbitrary transformation. Now, we can ask ourselves, how does H change under G? We can also ask ourselves, well, what is H prime if it's given by H plus the Poisson bracket of H and G? So that's how H changes. So now, if H prime is equal to H, so we say that H is invariant with respect to the transformation generated by G. So if H prime is equal to H, then from the equation that we have that H and G, the Poisson bracket of H and G must be 0. But that also means that the Poisson bracket of G with H must be 0. Right, that's one of the properties, that the Poisson bracket of A and B is equal to minus the Poisson bracket of B and A. So if it's equal to 0, then they must both be equal to 0. But we just said earlier that the Poisson bracket of G of something with the Hamiltonian is 0, that something is conserved. So if the Hamiltonian is invariant with respect to the transformation generated by G, then G is conserved. That again is an amazing result. I can take some completely arbitrary function G. Out of that function, I can create this random transformation of the coordinates. Then I can check to see if the Hamiltonian has changed, and if it hasn't, then G is conserved. So we see this, again, this relationship between Hamiltonian, conserved quantities, energy, translations in time. It's all related. And the Poisson bracket's another tool to dig into that. And it's important because the Poisson bracket is a relation to quantum mechanics. That's how you go from classical mechanics to quantum mechanics. there's a prescription where you convert Poisson brackets into commutators and you change functions of the variables to operators. And then all these symmetries and all that stuff becomes preserved in quantum mechanics. Any questions about that? There's a lot to absorb, right? So I encourage you to rewatch the lecture online and read the notes in detail. Right? I don't expect you would have caught all of this in the first go. But hopefully you're at least a little bit, it's piqued your interest a little bit. And that these Poisson brackets have important meaning. And that there's a relation between conserved quantities and that you can use those conserved quantities to generate the transformations due to those quantities being conserved. Okay. So now, we'll move on to the tutorial section. So assignment 5 is due next Friday. Assignment 5 has 5 problems. 2 of them on chapter 5, which I think are relatively straightforward, and they're covered by the summary that I give in the tutorial, the theory part of it. And then chapter 7 has problems related to the Hamiltonian and Poisson brackets. And since you have 0 practice with the Hamiltonian, that's what we'll focus on today. And so I'll let Michelle do one of the examples from chapter 7. That's going to be problem 7.1. I forgot to say that if you go to the Moodle website, you can see assignment 5 as well as the problem sets for chapters 5 and 7. And we're going to work through 2 examples from that problem set. And Michelle is going to start by doing problem 7.1. So let me figure out if I can give Michelle access. Michelle, do you want access to
I think
Michelle
it needs to be
or M2? So that's
the tablet.
That's the tablet. Okay. The moderator privilege. So you have to make sure, if you have 2 devices, you should make sure that you turn the
Right, I have
on
it on mute. Okay, so
But you also have to turn the speakers off.
What was that?
On one of them. You have to turn the speaker off on one of the devices as well, because otherwise it's going to pick up. You can stop sharing. Okay, so now you should be able to share.
And I want a OneNote. Hey, you guys see what I see? Yeah, all right. Here we go. All right, so 7.1 is our standard pendulum. I'm just going to draw this really quickly. You probably see it in your notes or the assignment. Come on. We have a rigid rod, which I really like because it means we don't have to worry about spring energy. And there's our theta. So the first thing that we're asked to do is find the general coordinates and write a Hamiltonian. So how many degrees of freedom do we need to describe where this mass is? And you guys are fairly familiar, we're constrained to the XY plane. And if we're constrained to the XY plane and X and Y are related through theta, then we have 1 degree of freedom. If there are any questions about that, speak now, and we can go over it more slowly. I'm going to choose my general coordinate as theta. And so now we need to do our Lagrangian. So our kinetic energy is equal to 1/2 mv squared, and our potential energy equals minus mg L cosine theta. And you can see if this is theta, then cosine is, of course, along the y-axis, and it is in the negative direction, which is why we keep the negative sign. V is R, and this can be kind of confusing. The pendulum floats in different directions, so R isn't equal to L, but it's related to L. Negative L cosine theta in the y direction plus L sine theta in the x direction. And then, of course, we're going to take its derivative with respect to time, and we have L sine theta, theta dot in the y hat direction plus L cosine theta, theta dot in the x hat direction. When we square this, the middle term cancels, and we end up with an L squared sine squared theta, theta dot squared plus L cosine squared theta, theta dot squared. I forgot to square the L, sorry about that. And sine squared and cosine squared, of course, is 1. So now we have an L squared theta dot squared for our velocity squared term. So T is equal to 1/2 mL squared theta dot squared plus mg L cosine. Oh, that's not T, that's L. Sorry about that, guys. Mine's in another place. L cosine theta. Yeah. All right. I'm going to leave that there. Are there questions so far about how I was able to get this? Your chat window's up, so you can chat with me if you need to. All right. I'm going to take silence as everything is good. Now, the Hamiltonian is equal to the sum of your Q dot and the momentum minus the Lagrangian. So in this case, our Q dot is equal to theta dot, and we have only one of them. And so the PI is equal to the partial derivative of the Lagrangian with respect to theta dot. And I'm just going to do this fairly slowly. I have a 1/2 m L squared. I pull the 2 from the theta dot, and I get this, and that is equal to the momentum. Therefore, the Hamiltonian is equal to the theta dot mL squared theta dot minus 1/2 mL squared theta dot squared plus m, oh, I'm running out of room, sorry about that, GL cos theta. So the Hamiltonian is equal to mL squared theta dot squared minus 1/2 ml squared theta dot squared minus mgl cos theta. We have to carry the negative sign through. So it's fairly obvious that we've got a positive 1/2 ml squared theta dot squared minus mgl cosine theta. And if you recall, this one is our potential energy, and this one is our potential energy and kinetic energy, and we're adding them. So our Hamiltonian is the kinetic energy plus the potential energy. Are there questions here? Okay. Well, we know we want to get rid of the theta dot and express this in terms of momentum. And in order to do that, let's see, need to express with respect to momentum. So from above, we know that the ml squared theta dot is equal to the momentum in the theta direction. So let's just solve that for theta dot. I'm going to square everything. And are there questions here? Okay. Now I'm going to substitute this into our Hamiltonian. I'm too close to the edge there, sorry. I don't have trivia to share. This is just manipulating the mathematics as they're presented. So now I have the Hamiltonian with respect to momentum, which is what we were asked to do. So we move on to Part B. And Part B says use the canonical equations to obtain the equations of motion. So we're going to use canonical equations to obtain the equations of motion. So the first canonical equation is with the theta dot. We're going to take the partial derivative of the Hamiltonian with respect to the momentum. And we know that the momentum, which is equal to the momentum over the mass and the length of the rigid rod. And then the second equation is when we take the derivative with respect to time of p dot. So we have this Hamiltonian and our angle, our general coordinate. And when I take the partial derivative of the Hamiltonian, I get mgl sine theta. Now I'm going to use these two equations and solve for theta. So I'm going to take the derivative with respect to time of equation 1. So that's a theta double dot is equal to our momentum term. And now I'm going to substitute the momentum term, that is the derivative with respect to time, the p dot, into our equation. So now I have a minus mg L sine theta and L squared. And you will all recognize this as the equation of motion for a normal pendulum or simple pendulum. Now we go on to part C. And we're asked to repeat part A and B. But this time the rod has a mass of m. So now we need to consider the moment of inertia. And you know, the moments of inertia differ depending on the geometry, and we are given, or you may have to look this up, I'm not sure, that the moment of inertia for a rod is 1/3 the mass times the length squared. So now we'll do the kinetic energy, which of course is T, and we have 1/2 mL squared theta dot squared plus 1/2 the moment of inertia times theta dot squared. And this is equal to 1/2 mL squared theta dot squared plus 1/2 times 1/3 mL squared theta dot squared. Are there questions regarding why I placed the moment of inertia in the equation as I did? I think that's a little bit tricky, and I'm really glad that we went over this. I am just rearranging. Hope I did that right. You guys check my math. And now we go to the potential energy. And of course, this time we have to consider the fact that we have a rod with mass m. Here's another little tricky thing. I assume that the mass is distributed evenly across the rod. It's not heavier on one end than the other, except for the mass that we're already accounting for, of course. But the rod itself, the material, is consistent in the same size, which allows me to divide the length of the rod by 2. So basically doing the average mass by doing the average length of the rod. And this is equal to minus G L cosine theta times the mass at the end of the rod plus the mass of the rod divided by 2. Now we're going to do the Lagrangian. And this is equal to 1/2 mL squared theta dot squared times the mass of the ball plus the mass of the rod. Oh, that's a 3. plus GL cosine theta, mass of the ball, plus the average mass of the rod, and we have the momentum then is equal to partial derivative of the Lagrangian divided by the partial derivative of the time, theta dot, is equal to, and again, I come through, you guys probably don't have to do it this way. I just like to show everything, and I do the same thing for myself in the privacy of my room when I'm doing homework. It eliminates mistakes if you show all your work. I know sometimes it takes longer, but I find that it's worth it for me. It might be worth the extra step for you as well. Now I'm going to square this whole thing because, of course, we're going to, we have a theta squared in the term, not just a theta. So theta dot squared is equal to our momenta squared, L to the fourth, m plus squared. And now our Hamiltonian is equal to the kinetic energy plus the potential energy. We equal 1/2 L squared theta dot squared m plus minus GL cosine theta m minus m over 2 . This is where we're going to make our substitution. Cosine theta m plus m over 2 . Theta dot, oh, sorry, I don't want to do that yet. I want to do some cancellations. There's your Hamiltonian. so I guess I want to ask, are there any questions? I lost one computer, so I still have the tablet on, however. I'm hoping that you can hear me.
Yeah, it's working fine. I can.
Good, okay. Are there any questions? Reconnecting so that I can see your questions. I think this is really cool that we can use the Hamiltonian, and you can see when you add the mass of a rod, there's only this term that differs. Oh, wait a second. Yeah, because if you solve for theta, you'd end up with the same equation of motion, except you'd have the masses involved there, both masses instead of just one. Looking over everything, are there any questions? Clear as mud? Okay, well,
If there's no questions, then I could do the 7-4.
yeah, I guess so.
All right, no more questions for Michelle? All right. I think you have to stop sharing so that I can take over.
Yeah, there we go. Where are you? There it is. Okay.
Okay.
Is control back to you?
Yep.
Okay, good.
All right. Thanks, Michelle.
Yeah, thank you for the opportunity. Appreciate it.
Okay. So I'm going to do another example of using the Hamiltonian. This is problem 7-4. And so again, it's a problem that you visited before. I think both with D'Alembert's principle and with the Lagrangian method, and so let's do it now with the Hamiltonian. So this is our spring, pendulum with a spring on it. Huh? So I'll let you guys make a quick drawing for yourselves. Not going to be as good as what I can hand draw here. And then we'll get started. So this is a problem with 2 degrees of freedom. And so I'm going to choose R and theta. So theta I've already drawn, and R I'm going to take as the distance of the mass to the origin. Okay, so as usual, this is a massless rod. It's only there to constrain our bob mass m to move linearly. Okay. So step 1, so we're asked again, right, to solve for, present the Hamiltonian and then solve for the equations of motion using the canonical equations. So in this case, the kinetic energy is given by a half m. So the coordinates that I've chosen are polar coordinates, and we've shown this before. So I'm just going to write out that the kinetic energy is half m times r dot squared plus r squared theta dot squared. If that's not obvious to you, you should go back and look at your notes. You derived it in one of the assignments, and we've done this problem before. I'm also going to write the potential energy. The potential energy has two terms in it. So the first term is going to be a spring energy. So the spring has a rest length of L. So the amount that the spring is stretched or compressed is R minus L. And so the potential energy from a spring is a half K and then the compression length squared. We also have gravitational potential energy. So since Y is pointing upwards, gravitational potential energy is plus mgy, right? So in this case, Y is negative, right? So where I've drawn the pendulum, the Y position of the pendulum here is minus R cos theta. So the gravitational potential energy is going to be minus mgr cos theta. So it's plus mgy, but y is minus r cos theta. So this system has everything that makes it look like energy should be conserved. So I expect the Hamiltonian to be equal to T plus V. But let's say we don't know that to start with. So let's start from the more general definition, which is always safe, and that's to start with the Lagrangian. So the Lagrangian is T minus V. So T is a half m r dot squared plus r squared theta dot squared minus V, so it's minus a half K r minus L squared, and then plus mgr cos theta. So that's our Lagrangian. If I want to do the Hamiltonian, right, I need to know, for each degree of freedom, I need to know the conjugate momenta, so I can do the sum of the conjugate momenta times the degree of freedom velocity. So ultimately, I really need to know what PR is. So PR is defined to be di-L by di-R dot. So the conjugate momenta to the R coordinate, di-L by di-R dot, and if I look at my Lagrangian, I only have one R dot in there. That's the first term. And when I do di-L by di-R dot, I get M R dot. Eventually, I'm also going to need to get rid of R dots in favor of PRs. So I'm just going to write that now. I can tell that R dot is PR over M. So later when I have to get rid of R dots, I can go look up this equation. The other one that we're going to need is P theta. P theta is defined to be di-L by di theta dot. If I do di-L by di theta dot, I only have a single theta dot in there. And when I do that partial derivative, that's the second term of the kinetic energy, I'm going to get m r squared theta dot. And again, I know later I might have to get rid of theta dots and replace them with p thetas. So I can tell here that theta dot is going to be equal to p theta over mr squared. So in principle now I should have everything I need to calculate the Hamiltonian. So the Hamiltonian H is given by the sum over the degrees of freedom, so there's going to be 2 degrees of freedom, of Pi Qi dot minus L. So the sum of the degrees of freedom, so I have the first one is R, so it's going to be PR times R dot, right? So PR, so that's M R dot, that's PR, and then R dot is R dot, obviously, so that just squares it. The second term is P theta, so that's M R squared theta dot, multiplied by theta dot, that just makes it squared. And then it's minus the Lagrangian, so it's minus a half M times R dot squared plus R squared theta dot squared. Then it's plus a half K R minus L squared, and then it's minus MGR cos theta. So as often the case, I can combine the MR dot squared that I have at the front with the minus a half MR dot squared that I have from the Lagrangian. So that gives me a half MR dot squared. Same thing happens with the theta dot squared, so I have plus a half MR squared theta dot squared. And then I have the two potential energies, so I have plus a half K R minus L squared minus MGR cos theta. That's the value of the Hamiltonian, but it's not the correct way to write the Hamiltonian, right? The Hamiltonian cannot have variable dots in it. It must have variables or coordinates and momenta. So I need to get rid of the R dot squared and the theta dot squared in favor of PRs and P thetas. And of course that's why I wrote them up at the top there. The other thing I want to point out is if you look at the Lagrangian, it does not depend explicitly on time. It's quadratic in the velocities, and the potential energies don't depend on the velocities. So I should have expected that in this case, the Hamiltonian was going to just be equal to T plus V. So I could have saved myself a bit of a step there by simply switching the signs in the Lagrangian. The signs in front of the potential energy terms, right? It's exactly the same as the Lagrangian, except I have plus a half K and minus MGR. All right. So rewriting now the Hamiltonian, so we replace theta dot squared with P theta squared over M squared R to the fourth, I believe. Let's go and check that out again. Theta dot squared is P theta squared over M squared R to the fourth. And we'll also replace R dot squared with PR squared over M squared. So if I do that, my Hamiltonian is a half M. So now instead of R dot squared, I have PR squared over M squared plus a half M R squared theta dot squared. And now instead of theta dot squared, I'm going to write that as P squared theta, the P theta squared over M squared R to the fourth. And then the other two terms are the same. So I have plus a half K R minus L squared minus MPR cos theta. Simplifies a little bit. So I have an M in the first term that I can cancel in the denominator. So I have a half PR squared over M plus a half P theta squared, cancel an M and an R squared, so I have P theta over MR squared, and then the last two terms are the same, a half K R minus L squared minus mgr cos theta. Okay? That's it. That's my Hamiltonian. So that's all that. And then part B. Are there any questions about that? Part B is to write the canonical equations, to get the equations of motion. So I have 4 variables, right? So we want the canonical equations for R, PR, theta, and P theta. Remember, the P's are to be treated exactly the same as coordinates. We have 4 different things now. In the Lagrangian formalism, we have 2 degrees of freedom, and we describe our system using R and theta and second-order differential equations for R and theta. In the Hamiltonian formalism, we use R and theta and PR and P theta, and then we only use first-order differential equations. Now I have to do all the canonical equations, remember? So the canonical equations are that Qi dot is di H by di Pi, and Pi dot is minus di H by di Qi. Okay. Alright, so I'll do R dot. So R dot is di H by di PR. Alright, well that's easy, right? There's only one PR in all of H. And so if I do that, I get PR over M. And is that surprising? Well, no. Actually, we already knew that, right? From doing di L by di R dot, we already knew that R dot was PR over M. But we wouldn't have known that if we just, well, actually we would have known this, yeah, no matter what. So the first canonical equation, the one for R dot, ultimately you just recover the transformation between R dots and PR. Remember, we removed the R dots from the Lagrangian, or the Hamiltonian. So it makes sense that we can get them back. Then we have the PR equation, alright, so that's going to be PR dot. How does the momentum in the radial direction change with time? That's minus di H by di R. Okay, so I look at my Hamiltonian. And looks like I did it wrong on my notes. The terms that depend on R, the last 3 terms all depend on R. So the first one I have to do is a half P theta over MR squared, right? So di by di R of that. So the half P theta squared over M doesn't depend on R. Let's take that out. And then I have d by dr of 1 over R squared. So that's going to give me minus 2 over R cubed. Then I have to do di by di R of half K R minus L squared. So if I apply the chain rule, I bring down the 2. Then I have R minus L. And then I have the derivative of R minus L, which is just 1. And then the last term, it's minus mgr cos theta. And then d by dr of that is simply minus mg cos theta. that's the equation for PR. Alright, you can cancel out the 2's there in the first term, but it doesn't really make it any simpler. Then we want theta dot. So theta dot is given by di H by di P theta. So if I look at H, there's only one P theta in there. So di H by di P theta is just going to be P theta over MR squared. And then finally, the equation for P theta dot, that's minus, oh, I forgot to put the minus sign in the PR equation. There's an overall minus sign in front of all of this. Alright? Sorry about that. P theta dot is minus di H by di theta. It's minus, where the theta is in the Hamiltonian, only the last term has a theta. So that's going to be confusing. There's a lot of minus signs that are going to flip around. So d by d theta of minus mgr cos theta is plus mgr sine theta. So there's a minus sign in front from the minus di H by di theta, but then it's plus mg sine theta with a minus sign in front. And that's it. Any questions about that? This is an example of using 2 degrees of freedom. The one you have to do in the assignment has 2 degrees of freedom. So you should be able to follow the methodology. Okay, so if there's no questions, that's it for today. The assignment is due next Friday. Okay, thanks everyone. Talk to you all on Tuesday.